Okay. Hi, everyone. We're finally ready. So we're going to listen to the presentation of Akhil. So he's going to be presenting work that appeared at the IJCNN this summer. So please go right ahead, Akhil. Yes, go.
Okay. So hi all, welcome to our presentation on semi-weakly supervised method detection for by sampling pseudo-ground-truth boxes. This is a joint work with our team at LIVIA and Heatmap, whom we are in the entire solution. So this is and the overview of our discussion today. First, we'll present the motivation, general motivation of going for this weekly supervised setting. And semi-weakly supervised setting, and then we'll present the existing solution stack in the weekly and semi-supervised.
See. I think it was new.
Okay, so maybe we could start over. On now, you could put on your camera too.
Okay.
Perfect. Excellent. Okay. We're on.
Okay. Yeah. Okay. Oh, okay. Sorry for the interruption. So again, this is the overview of the discussion. We'll start with the general motivation of the settings and then present the existing solution stack in the weekly and semi-supervised paradigm. And then we'll see the proposed approach and how it incorporates the best of these things. And yeah, then we'll see the empirical result from our model, plus later on a discussion of its benefits and shortcomings and conclusion. So the general motivation for these settings is basically like obtaining the dense annotation is really costly. As you can see here, going from the image level to instance level, like from bounding box to bounding box, and then the pixel level annotation, this increases our annotation time, and this is really not scalable for all of the detection problems that we want to solve. So in general, the community is interested in like how you can do how you can make detectors with less dense annotations. This is basically the fundamental approach of fundamental motivation of this weekly and semi-supervised methods. And now we'll see what is the settings. So when it comes to weekly supervised settings, we have images with image level labels, and we try to learn an object detector from this. So the essentially what we have is the data sufficient for doing the classification. So that is why it's weak supervision, because for detectors we need the bounding box level information, and we try to learn with this classification level information how we can learn an object detector. Because as we've seen, like this annotations at the image level are cheaper to obtain. And in the semi-supervised settings, we have a few labeled images, and then a large pool of images are supplied without any labels. So for the labeled images, we have instance level annotation for each of the instances. So now we'll see how the general, how the common solution stack in this different settings. So for the weekly supervised detection, what we do is, like as we have seen, we have a classification level information. So we compute the expected classification class score for each, and then we optimize this. We optimize this classification loss. How we do this is basically, suppose in an image we extract thousands of object proposals such that they'll cover like most of the object instances present in the image. They'll be of various scale and aspect ratios, and this is usually obtained using techniques like selective search and box, etc. So finally, what you have is like proposals all over the image, thousands of them, and then you have to do an expensive ROI pooling evaluation at each of these locations, and then sum up their scores, and finally get the class score for each class present in that image. And then you optimize this with the classification loss. And usually what they do is like this is the common first stage. And in recent days, they have discovered that if you get this pseudo-ground, if you get the prediction from this weakly supervised detector and use it again to self-train using those predictions, one step training, it will generally improve the performance of the detector. That is basically 2 stages of training. But in the second stage, you use a standard fully supervised architecture and use the detection from this thing as the input for that one. Yes, so this is the common solution that we use in this weakly supervised settings. Now, when it comes to semi-supervised, most of the, the popular approach in these days are revolving around this mean teacher idea, where you have a teacher which is learned with the exponential moving average weights of a student. So in this case, as we saw here, the labeled images, it goes to the student network as usual, and then you can compute the supervised loss. And for the unlabeled images, we create 2 augmented versions of that, weak and then the strong augmentation. The weakly augmented version goes to the teacher, and it will give the pseudo-ground-truth. Basically, like what you are getting is the output of the teacher network, and then you do some post-processing and use it as a pseudo-ground-truth. And this is used to supervise the strong augmented version, which is passed to the student network. So this basically has these 2 networks, where one you don't learn by backpropagation, but still 2 networks, identical copies in structure. And this has to be trained with extensive data augmentation to have some really good results. And as a general case, this EMA based learning are usually you have to train it very slowly. So these are some of the issues with the semi-supervised methods in the literature. So this is basically a general paradigm, but like what you see in the literature are like different flavors of this mean teacher idea. So now we have seen these 2 cases, and we look at this semi-weakly supervised settings. So here we get the labeled images, a few labeled images similar to the semi-supervised case. And what is the difference is for the unlabeled images, we have weak image level annotations applied. So these are like global cause annotation, which we can basically easily obtain. And then the idea is basically how we can make use of this mixed supervision settings to learn detector efficiently. Now we'll see how we approach this problem in our settings. So what we have is a sampling based approximation and sampler based solution. And here is the general overview of our settings. So if in the top part with the green dashed lines, you can see what goes when it is a fully labeled image. So it just the normal process, it goes to the detector and you compute the standard classification detection loss, and that is what it happens for the fully supervised string. For the weakly labeled images, assume that we have for the time being, assume that we got a set of object proposals in this image, like in the weakly supervised settings that we have presented, and we have a memory which stores these object proposals and a score for each of them. The score is basically initialized to 0 and then it is learned over the time. So now there are two critical components that we used here to facilitate this learning in these settings. One is the sampler, which basically samples a set of pseudo-ground-truth boxes for each object as specified by the weak label. So in this image, it is been said that there is a host and then there is person in that image. So the sampler will sample a few boxes for the host category and then a few boxes for the person category. And this is being used as the pseudo-ground-truth, and then it goes to the detector. So it can process the same way as the correct ground-truth and get the detection and scores. Now, this is the second component. Second component is this score propagation. So what it does is basically it uses this detection scores from the detector and update the scores of these object proposals, which we have in the memory. So this two process goes on at every iteration. And what we observe is that over the time, the scores accumulated for these object proposals, they'll be like really representative of the semantics of that region. And then so though we sample randomly in the beginning, the sampler due to this score propagation process, it will accumulate good scores at the object regions, which is semantically correct, and subsequently it will start sampling better from the correct regions. Now we'll see how these two components works in detail. The sampler is basically what we use here is an importance sampling. So I'll just briefly present this idea of importance sampling. So the theory of importance sampling says that suppose we want to estimate the expectation of quantity from a distribution P, and if you say you try to do it with the Monte Carlo approximation, and if the P distribution is difficult for you to get samples from, then it will be really difficult for you to get that estimate properly, and that need probably a lot of samples and it will be difficult. So in this case, like the figure on the right, suppose I want to estimate the tail probability of that shaded region from the P of X. If I want to do it within a good standard deviation, good variance range, I probably have to sample a lot of samples from this P of X to get these things done, because most of the samples will be outside of that region, and it'll be a lot of time taking to get that estimate. But if I can get this at a distribution Q from which I can easily sample from, and then what I have to do is I have to do a correction on the fact that I'm not now taking the sample from this P distribution, I'm taking it from the Q distribution. So that correction is basically the ratio of these densities. And so what it says is that if you can do this correction, and can sample from this Q distribution, which is easier to sample, then you can actually obtain an unbiased estimate of the quantity with this Q distribution. So this is in theory what importance sampling is doing. It's a variant of Monte Carlo approximation. Now we'll see how we make use of this thing in our settings. So as we have seen for the weakly supervised settings, there are these proposals which is spread out all over the image, and then this is how we compute this expected score for each class. The first formula. Now assume that with I have this Q distribution, which which here is basically obtained from this accumulated score of the object proposals. So what I see is that if I can estimate this ratio of densities, then I can sample from this Q distribution and approximate this scores, which is what the weakly supervised detectors optimizing. So our idea is basically those samples which we use to approximate these scores, those samples are used as pseudo-ground-truth, and then we compute the classification and localization laws of the detector. That's how it happens in our settings. Now I'll show how this Q distribution is formulated in our, and how this Q distribution is computed with this score propagation thing. So here you have this yellow boxes, which are the detection, and then the red are the object proposals. What we want to do is to propagate the score of the detection boxes back to the object proposals, and then we have to do it at every iteration so that it keep on accumulating the score for that region for a long time, and then later on it will become more and more correct. So how we do this is basically based on the overlap between the detection and this object proposals. This is the equation that we used to update the scores. It is 1 minus IOU times the score of those proposal, the previous score, plus IOU times the score of the detection box. And yeah, this score, basically we start with 0 initialization and keep on accumulating it as the detector is learning. So this basically is different from the P distribution that we used here, which is evaluated at the current time. But this closely approximate the score, and then we see that it's doing a right job when we sampling from those locations. Now we see that how this is stored in the memory. So these are the proposals, that suppose these yellow boxes are the proposals, and assuming we are only concerned with these two classes now, person and host. So in the memory, we have these proposals, and we have the scores updated for each iteration, and there is a score for the background category also. And this, we use this scores and do a softmax sampling from this distribution that we can get from the scores. So if I say that there is a person in that image, I take all the proposals person scores and then sample from that, like say 5 samples for the person, and then compute the classification and localization laws. And here I show a demo of how this is evolving with the epoch. So right from the beginning, it starts at random location because the score is initialized to zeros. And as the time goes, it kind of converges to some meaningful location for this class. Now we'll see this learning algorithm in detail. So this is the data that goes into our method, weakly supervised methods with the object proposals. And for those weakly supervised weakly labeled images, we get this sample locations and their class labels. And the next stage is computing the detections, scores and detection boxes. So in a batch, you can have both weakly and labeled images. And for the first case, like when it is weakly labeled, you do sampling, and then finally you can detect for both and then get this detection and scores. And then only for the weakly label case, we update the score of the proposals in the memory with the score propagation component. And then here we'll present the empirical results from our study. So first we want to make sure while designing this score propagation thing that we are rightly accumulating the semantics at the right location of the object. So to check that, we compute, we visualize this heat map. So here in this case, for each proposals, for each class, I get the score for each proposals, and then I do a normalization and then visualize this thing at the image level. So as we can see that the region where the proposals are having higher scores, it corresponding to the correct object category in many cases. So it spreads out sometimes here and there, but roughly you get something meaningful due to this score propagation process. And then the next thing that we checked is how this design is improving the generalization. So for that, we compute this performance at different level of supervision. Here we use the Pascal Pascal VOC, and I vary the amount of supervised samples, and in the red curve, I plot the mean average position, which is the metric standard usually used in the detectors. So in the red curve, I plot what is the performance when I use only those labeled samples. And in the green, we have the results when we use both the labeled and then the remaining as unlabeled, remaining as weak labels. So as you can see there, the generalization is improving when we use weakly labeled images, and it generally shows 10% improvement in the beginning, like 10 to 20%, and as more and more strong labeled images are coming, the gap reduces, which is normal. And here we did a comparison with other methods. So this is the standard table where we put the metrics and then compare with the relevant methods. A lot of them are semi-supervised also. And for our semi-supervised case, what we did is we trained a classifier using the available label data, and the prediction of that classifier is used as the weak label for our semi-weakly supervised case, and that's how we got the semi-weakly supervised and semi-supervised results in our settings. And this is the comparison, and then we also see that our performance gets close to the upper bound where we provide all the annotations. And here we have some detection results from the VOC 2007 test set. Next, we try to see the error analysis of this type of detectors. So in the right is what the error diagram that and there are different type of errors, like localization error is, the localization is less than that threshold, which is 0.5. And then there are missing missing ground truth, which is that some locations where we don't have any detections, but actually has a ground truth. And then classification error is there, and then confusion with background, and different categories of errors are there. So what we see is most of our error is from localization, which is quite usual for all these semi-supervised methods. But another interesting observation is that there are a lot of missing locations too in our method. Missed objects are, I think we expect that it is probably because of this sampler is failing in some locations, in a sense that the scores that we are accumulating with the heat map that I have shown here, if there are many instances of the same class, then what happens is that some of the dominant objects which can basically accumulate all the scores. If there are smaller objects of the same category, they probably may not get better representation, better score accumulated over the time. So there is a probability of missing those locations in the sampling process. And in some cases, we have observed that is happening. So that's one way that we found that it can fail. So to summarize our discussion, we presented this sampling-based semi-weakly supervised learning setting, semi-weakly solution, and we compared this with weakly supervised, other detectors. So regarding the weakly supervised case, what it eliminates is that because we do this sampling and evaluation only at those sampled regions and around, we don't need to evaluate the proposals all over the image, and that saves a lot of computation. And it also eliminates the need for that two-step learning, because this we use as the pseudo-ground-truth and then compute the standard loss of a detector. So there is no customized first stage where you learn with a different architecture and things like that. And compared to semi-supervised, we get away with this mean teacher things with the two networks and a lot of complicated augmentation pipelines, and that we see as some of the merits of our solution compared to the standard semi-supervised cases. And then we also saw the some of the limitations of our method of regarding that exploration, getting stuck at some dominant regions and things like that. And right now what we used is a fixed set of proposals. There we also think that it will be better if the proposals can be updated with the better detection boxes, because as the detector is learning, we could probably get better detection boxes that can be added to this pool of proposals, and probably it can also gain performance a bit. Yeah, that's it. Yeah.
Thanks, Akhil. I'll talk through your computer.
Okay.
Thanks a lot. I'm just wondering if there are any, I don't see the people. I'm wondering if there are any questions from the audience. So if you're at your place or somewhere else, maybe turn on your camera and we can ask questions. Or
hello, guys.
Hello.
Hello.
Are you hearing me well? Hello, everyone.
Yes.
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 First of all, I would like to thank you for this great presentation. And my question related to the proposal itself in slide number 11.
Okay, just 1 second. Yeah.
Well, concerning the updating the score, how you update the score using the score propagation? Used what here? How you update the scores?
The score updation is basically based on this equation that I present in this slide. Suppose I have initial at the beginning, I have a S0, which is initialized to 0. And then I got a few detection boxes in that image. Then I compute the overlap, which is the intersection or union between the detection box and this object proposals. And what I do is, like, I select for each subject proposals those detection boxes which has the maximum overlap, and then propagate its scores based on what is the overlap between those two.
I mean here, how the iteration will arrive to take it the most closed region you want. It means in the iteration, how you will be sure that the update will go in positive way, not in negative way. So how you will be sure that your updating score will improve the accuracy or improve the, let's say, the rate of detection?
So this detection is basically like the scores are updated, like, you know, in throughout the learning process. So what I see is that, like, though in the beginning it can be random, like it may not be like a correct representation, but as and when we learn it for many epochs, it will start get something meaningful semantics for the locations.
Okay, I see. Thank you so much.
More questions from here, or
Maybe
From-
about the memory, like you have the sampling memory table for the
Yes.
proposals, right? Like
Yes.
how is that, like for each image you have set of proposal, or what is the structure of that?
The set of proposals are fixed. Usually, suppose there in the weekly supervised also we get around 2000 proposals in an image. They stay fixed, and what we have is in memory a score matrix. So that is, suppose we are 10 classes, then 10 plus background is 11. So
those
the
2000 are, how do you fix at the beginning, like their coordinates?
we get this usually from selective search or edge box kind of method.
Like
These
for
are like
each image, okay.
yeah, for each
Okay.
image. These just classical image processing techniques. You don't need any supervision. You can
Yeah.
just compute it, store it in memory. And this core matrix will be, that is a matrix of 2000 crores if there are 10 classes, 2000 crores 11, 10 plus 1 background.
And is there any like changes in the performance if you reduce the 2000, like vary the size, like 2000 to 1000?
Yeah, there will be. It basically depends on the recall, right?
Yeah,
Suppose when I'm using 2000 proposals, I get 90% of
Yeah,
recall,
yeah.
and then it is good. If I cut 2000, the recall goes down. That means I don't have good proposal for
Yeah.
many locations. It can go bad, and that is why I think if we update also the set of proposals when the detector is learning, probably it can also
Update the
get,
set of proposals in the,
because I keep the
Okay.
2000 as fixed, right?
Fixed,
I
yeah,
don't
yeah,
change it
yeah,
while learning. But in semi-supervised, because your teacher later, the teacher is giving you the predictions, it can be dynamically
Okay.
changing. That's one aspect.
I have a question. How do you select the samples that are labeled and those that are non-labeled in the semi-weekly approach in your experiments? How do you
The
select?
experiments actually we demonstrated with random
Right.
selections. Like suppose when I pull out that curve 10%, 20%, I just select from Pascal VOC 20% of the labeled images, and then the remaining as weak labeled.
Okay. If you're running a setting where that would look more like active learning, and you were able to select the ones that were annotated, were labeled, as opposed to the ones that were unlabeled, can you think of a strategy or a criteria you would use to make that selection?
In the context of active learning, I mean, in generally, I think we want something that will cover a lot of variations in the same object category, like different variations and things like that. And I don't know how we can formulate immediately that. But generally, I will be motivated to find some diversity and other aspects in the samples that I pick the label for.
Okay, fair enough. So you'd want to find informative images or bounding boxes that can.
Yeah.
Okay, that's good. That's good.
Okay, excuse me. It's the same question. The same question as Eric. I want to, if it is possible, to say what is the criteria you identify the semi-labeled or fully labeled the image you have. I mean, how you decide this is weakly labeled or semi-labeled or fully labeled and etc. So what is the criteria, in fact?
So right now for the empirical studies, we use the random, we use the from the available set, like randomly say 10% is labeled and then the remaining is unlabeled. This is the same settings that we see in the semi-supervised literatures also. I think the general motivation is to say that you can be very loose about the criteria and still we are good because we improve the generalization. I think that is how they try to show it. And so I followed the same thinking. I didn't try to get any strategy for like how I select this 10% from the available pool. And
So just to understand a little,
Hmm.
you mean in let's say semi-label, it means you take a part of real region or the region ground truth. Is it, what do you mean in semi-labeled? Fully labeled, okay, it means you detected the full object inside the image. Okay, semi-labeled, what do you mean? You take a part of the object?
so if it is semi-supervised, what I mean is that I have a few set of images for which I have the bounding boxes
Right.
and then at the instance level labels, but the large chunk comes without any labels. And in our settings, what is the difference is that this large pool, we also have the image level labels, the tags, simply you can say, but the labeled pool is in the same proportion. But here we use the weak image level annotations. And as in the empirical studies, we also show that you can convert this for semi-supervised also by training a classifier with the label samples and use that classifier to give the weak labels. But that is slightly lower in terms of performance.
So there is no clear criteria what is the weakly labeled or fully labeled, right? Means there is no criteria, for example, percentage of the object equal 20% from the full object. This could be, for example, the weakly labeled, something like this, right?
For the splitting, we don't have any criteria. We say just
I see.
random.
I see. I see. Thank you.
I guess it's a given of the application.
Yeah.
Yeah.
Mm.
Okay. Any other questions online or from the hardcore audience that came today?
If there is no question, you can continue, ask.
Hang on, give me a second here. I've got one. Like, what is the overhead of this? Because it's clearly like you use a sampling, you're proposing a sampling approach. And although it's very interesting, you're adding complexity, right? So I'm just wondering what it adds in terms of the complexity for training. Like if you had to train a detector with weak labels, would it take you a lot longer than training a detector if you had all labels, or if you had the bounding box annotations and classes and everything?
You mean the general case of weakly and fully supervised?
Yeah. Is it much more complex in terms of training?
Yeah, like we have seen that the process has this evaluation of object proposals at every locations, and then that is basically the first part, and then you get a set of detections, that is the pseudo-ground-truth. And here you also use that two-stream architecture, which is popularized by this WSDDN paper. And once you get the output from this thing, you pass those as pseudo-ground-truth, and then again train a standard detector architecture. So that means
There's quite an
two
overhead.
times training to get the best sort of performance in the weakly supervised case.
Okay, that's fair enough. I mean, it's the price you have to pay for not having labels. I guess.
Yes.
Okay. Sorry.
Mm.
Are there any other questions? I think so. Monsieur Shadad? No?
Yeah, if you want, yeah. I think there's 100 of medical imaging application could be used here. So what do you think, how we can apply this using the medical application? Let's say, for example, there is something called, let's say, about cancer. There's something related to lung cancer. And in the lung cancer, there's small spot called, let's say, nodules. And usually, until now, there is no real solution for such application. So how do you think that this method could be applied for medical application? Because we need to detect all the nodules inside the lung.
I guess generally you have very less number of classes than in the generic case that we see here, and there are a lot of papers which I see that use weakly supervised segmentation approaches,
Right.
and I guess they all use some sort of image level labels. So what I see is like, if you want to solve this in the semi-weakly supervised, you can collect all those images with that weak labels, which I also understood that like in medical image also you can say like this is cancerous and this is not. Like those labels probably you can easily locate. I mean easily provide than the segmentation at this image. So I can take a lot of such weak label cases and then a few samples. If you have the correct annotations, I can make use of this mixed supervised settings and then try to train it for the 2-class settings, I guess. Yeah, in that way, it can be a direct translation. Yeah, but more things can
Yeah,
be.
could be.
Yeah, in general, like you can basically use the less supervised data points also in training a better localization thing.
Okay. Are there any other questions from the audience or over Zoom? So if not, I think we should end it there. I want to thank Akhil for giving a nice presentation, and also, of course, if you have other questions, you can ask them offline. But thanks, Akhil, for presenting. And I guess we'll see you next time. I'm not sure if we're going to have seminars at the end of August, but probably we'll start up in September with a whole new set of presentations, and we look forward to seeing you there.